Hey, all right. So we should be recording. Is everyone still able to see the screen? It should be Ashley Noreen's yearbook picture. Hopefully you can see it. All right. Oh, people are leaving. Uh-oh. Okay. I'm assuming you guys can see this. Normally, oh, there we go. Okay, awesome. Thank you. So normally, I start out with a meme that, has something to do with design, to remind us what we're doing in 4501. This is one that I've used, in the aftermath of the first peer evaluation, which we've just gotten through for the ideation design report. And so I'll just read this. So this is obviously a yearbook photo. And what the student is saying is, when I die, I want the people I did group projects with to lower me into the ground so they can let me down one last time. And interestingly, Dr. Nemi says the same thing in MEC 3, so I think I can get away with it here. So really just the point of me showing you this is to let everybody know that we've gone through the peer evaluation. The peer evaluations were actually very good this time around. And when I say good, I mean, we usually have a couple of students who are a full 2 standard deviations below the average. And if you guys remember, way back in the beginning of class, we went over the syllabus. Being 2 standard deviations below the average on 2 peer evaluations over the span of the class is a violation of one of our course policies and will lead to getting a failing grade in the class. So not to be super overly draconian, but we have that mechanism in place to prevent students from free riding, and we have another mechanism in place to prevent students from ghosting their teams, because in the past what has happened is people have sort of gotten through the RER with a reasonably good grade, they've been assigned to a group, and then they've literally just like disappeared. And there was no mechanism for us to kind of single them out individually and say, you're no longer contributing to your group, and so you're out of the class. So just as sort of a reminder that those mechanisms are still there, in case anybody starts to falter in their performance. Now, I will say that there were a couple of students who were like right on the edge. They weren't a full 2 standard deviations below, so they aren't getting the nasty gram email warning from me. But the expectation, now that you sort of know the chemistry of your group and you know how everybody works together, is those peer evaluation scores should be going up rather than going down for the remainder of the semester. So just wanted to kind of remind you guys that is out there, and there are consequences for not supporting your teams through the next couple of weeks into the final presentations. So I wanted to mention that. And I feel like there's something else that I want to say. Oh, yes. The other thing that I want to say is I've sent around both a request in Microsoft Teams and an announcement, I think on Canvas, reminding everybody or letting everybody know that we are looking for undergraduate learning assistants, ULAs, for the spring semester, for spring 2023, for MEC 2. And so if you guys enjoyed the class and you'd like to continue working with me and the teaching team in a teaching capacity rather than a student capacity, we have it's something like 2 or 3 slots open. Now, just full transparency, I usually get something on the order of 30 to 40 applications. So the application process is very competitive, but it'll give you an incredible chance to continue contributing to the class, working with your near peers who are taking the class in the spring to help them through both the RER and the design process, get some teaching experience, and really make a positive impact on the final year of some of your peers and colleagues, their time here at UF before they graduate and transition into practice. So if you're interested in being a ULA for the spring, shoot me an email, mtraum@ufl.edu, and then I'll get you connected to the next step in the process, which is the formal application. So, okay, those are the 2 things that I officially wanted to say before the start of class. So let me jump to the first slide here and just kind of introduce this, and then I'll get out of the way and let Juliana take over. So just to give you like a little bit of history, about a year ago, we had a faculty colleague who co-taught this class with me. And she very rightly noticed that we were not considering safety anywhere in our Mech 2 design process. And Mech 2 is all on paper, so it wasn't that big a deal, except when we got into Mech 3 and the students were actually building the things that they were designing in Mech 2, we noticed that there were a number of like safety issues that students just didn't even bother to address. So things like pinch points, choke points, damage points, where people could get fingers stuck, or designs could actually damage themselves or other devices around them, or the end users or the customers. And so my colleague was like, oh, we need to add a presentation on safety to Mech 2 so that students are thinking about safety as they're doing the design process. And she was absolutely right to do that, which is why we've kept this in the curriculum even moving forward here. The challenge from before was the lecture was very much like a sage on the stage type thing, right? Where it was a faculty member just conveying knowledge down to the students. But there was no place in the curriculum where we actually assessed students' ability to take what was learned or what was taught in that lesson and apply it to actual design. So what we've done now is we have kind of a new version of this presentation, designing in safety, where we're going to walk through DFMEA, which I'll let Juliana describe in detail. And by the way, Juliana has worked at Cummins for multiple years, and she has actually done this process in an industry context, which is why I asked her to give this presentation rather than me. Because if I were to do it, it would be theoretical. But she's actually done it, so she's going to lead a discussion through DFMEA. But that's sort of the background as to what it is that we're doing today and kind of why. The last kind of comment before we jump into the presentation is so that there is a connection between what you guys are learning in the lecture and what you're expected to demonstrate in your design process. There is going to be a section in the final design report where we ask you to do DFMEA, a DFMEA analysis on one of the subsystems of your overall CSD design. So what we're talking about today will actually be something that we'll expect you to do in your final design report. And so that kind of closes the loop and connects the dots and makes sure that we're not just kind of barking safety rules at you, but that we're actually teaching you something that is then assessed later on in the process. So anyway, so that's the background. The place to start, though, to kind of tie this into all of the other stuff that you guys have been learning up until now, is to reintroduce to you the Kano model. And my hope, the Kano model was part of the creative ideation asynchronous course content. So my hope is that you've already seen this, and this is just kind of a refresher. But this is how I want to kind of lead in to the topic of safety in the context of something that you already know. So if you remember back to the asynchronous Kano model lecture, there's two axes in the Kano model. So one is the ability of your product to execute a particular need. That's basically the x-axis. And then on the y-axis is the customer response. And there's positive is up and to the right, and negative is down and to the left. And there's three essential kinds of needs inside the Kano model. So the most obvious one is the so-called performance needs. So these are things that are stated in the customer need statement, and typically more of these is better, or the better that you do them, the more delighted the customer is. So you can see almost a linear relationship here between needs execution and how happy the customer is. So can anyone throw out an example of what a performance need would be for our CSD design?
Launch speed.
Okay, yeah, we've heard launch speed as one possibility. Yeah, so the better that the more accurate your launch speed is, right? Like the happier your customer will be. Another one that we've heard is earlier today was weight. So the lighter your design is, the happier your customer will be. So those are performance needs. Then we've got so-called attractive needs, which are typically things you guys have heard the quote from Steve Jobs, which is the customer doesn't know what they want until you show them. That's basically an attractive need. So it's something that doesn't show up in the customer need statement because it's something that the customer doesn't actually know that they want or need. And a lot of times these are sort of the extra add-on bells and whistles, the special things that differentiate your design from the other designs in the marketplace and make yours the special one that the customer will actually purchase. So this is in a way sort of tangentially tied to the hedgehog concept, right? Like if your hedgehog concept has some aspect of an attractive need, you can build an entire product basically around this attractive need and then attract customers to your product over competitors' products. But the way that attractive needs work is typically customers don't expect them, right? And so if you execute an attractive need and you don't execute it particularly well, it doesn't really have a negative impact on the customer's delight or satisfaction about your product, unless you do a really bad job. In which case then the customer starts to get a little bit cranky. But more often than not, just a little bit of an attractive need executed well makes the customer extremely delighted and happy and choose your product over those competitors in the marketplace. So kind of the classic example here is if you check into a hotel and they have like nice baked warm chocolate chip cookies right at the front desk, and they hand you and each of your guests a chocolate chip cookie, right? A hotel is not a bakery, but if they give you a chocolate chip cookie, you're happy and delighted and, you know, excited to go back to that hotel again and again and again because you got this chocolate chip cookie for checking in at a hotel. If your chocolate chip cookie had, instead of chocolate chips, little chunks of inedible plastic in it, well, that would be an attractive need that you didn't execute particularly well. And that might turn people off a little bit, but the hotel experience overall is really what they're interested in, which of course is a performance need. So for us, an attractive need might be something like the customer need was just a constant velocity that's set on the ground before the satellite launches. So an attractive need might be the ability to tune or adjust that launch velocity like in a flight, right? Maybe the mission profile somehow changes and you can adjust that velocity for launching or dispensing the satellites while the rocket is still in flight. So that would be an attractive need, not something that the customer said they wanted, but something that makes the product overall more attractive. And then the final one is here in green. These are the basic needs. So these are needs that must be met. This is basically the basic minimum that you have to achieve in order to even exist in the marketplace. And these also typically do not show up in the customer needs statement because they're things that NASA or customer in general assumes that we as the contractors that they've hired to design and build this product are already aware of. And so this is the segue from kind of the Kano model into safety, in that safety and both the safety of the user and the safety of the people doing the assembly and the manufacturing and so forth, all of that is just assumed to be part of the design process. But if you look at the customer needs statement, there's nothing in there about user safety or customer safety from our NASA customers, right? They're just assuming that we're not going to design a CSD that's going to, inadvertently, kill a bunch of astronauts. So it turns out that safety is a basic need. And that's how it fits into the Kano model. But then there's this whole kind of separate analysis technique, which is this DFMEA topic that Juliana is going to talk about here in a second. So I've got one more slide to talk about, and then I'll hand things over to Juliana, and that is just where this kind of safety and factoring in safety and designing and safety fits into the overall process. So you guys have seen this chart before. This is my chutes and ladders diagram of the formal engineering design process. And you guys are probably somewhere between 7 and 8, right? You guys are doing your down selection, and once your down selection is done, you'll be cementing your preliminary design in anticipation of the preliminary design review, which is coming up, I think, even next week. And so the earlier in the process you guys can start thinking about designing and safety, as you guys will see, the better in terms of reducing the overall cost of the development process. And so we like you to do that now at step 8 in the process, not farther on when things have already been set in stone, because as you guys will see, it becomes much more costly and much more expensive to make changes later on in the process if you start to think about safety, too late in your overall design process. Okay, so let me pause there and get out of the way and let Juliana take over the hot seat here. As I'm transitioning, are there any questions about any of this stuff that I can answer before Juliana takes over? Nope. Okay. All right. Then let me just stop the video and mute here so we can do the change. And then when the video turns back on, you guys will see Juliana. So 1 second.
All right. Can everyone hear me? Hello, everyone. So we're gonna go into the terminology, specifically for terminology for the FMEA, which is what we're kind of going over today. So FMEA is a failure mode and effects analysis, which is a way to identify and address potential problems or failures in their effects on the system and process before a failure occurs. In comparison with the root cause analysis, which is done when the failure has already occurred, the main purpose of FMEA is to prevent the failures from happening as early as possible. And there are multiple types of FMEAs available. There's design FMEA, which is what we are going to learn today. There is process FMEA, which is done usually later in their design cycle. And there are different other kinds. And they're widely used in their industry, including engineering, of course, their manufacturing, marketing for their reason, medicine, and other places. And then we have failure. Failure is a process in which harm can occur, and that harm can be related to anything. It could be people, it could be your product, it could be the product around it, it could be the environment, for example. It could be anything that can be damaged. Failure mode is a way in which that failure can occur. And the risk is a situation involving exposure to danger. Okay, any questions on their terminology? Cool. All right. We are going to dive into the FMEA, or we're going to actually look into the DFMEA, so the design of failure modes and effects analysis. And so why we're doing it? Because FMEA evaluates failures through 5 questions. What can go wrong? Why that would happen? What are the effects of their failure? How that can be prevented? And what insights we can apply to the current and future scenarios. And of course, it's really important for us as engineers to know how our products can fail and how we can prevent that, so that if we don't have any, for example, legal issues or any additional future redesigns or testings, etc. And why we're doing it is because the goal of design FMEA is to improve product and process reliability, quality, and safety, to identify and eliminate or reduce potential product and process failures, and very important one, to document and organize shared knowledge for current and future use. A lot of the time in the companies, you would be able to use the previous iteration of the design FMEA for your current one. That makes your workload a little bit easier. You also share this knowledge of the different failures that can occur between the different teams, so they're aware of that as well. But from my experience, companies don't really share that information externally. Dr. Trump said that it was a trade secret, most likely, and I would probably agree with that. No one wants to know how your product is going to fail. Then the very important one is reduce costs and problems later in the product lifecycle. So whenever we're looking at the design lifecycle, we can imagine an exponential graph where the cost depends on the time. So the further down the line in your design cycle you are, the more expensive it is going to be to redesign something, or create a new test or to remanufacture it. And that's why figuring out their failures as early as possible is very important, because of course, as engineers, we want to save money, or at least your company wants to save money, and we don't have an unlimited budget. Well, and of course, we have a better customer satisfaction as another goal or purpose of IDFMEA. When are we doing the design FMEA specifically is whenever we have a new product or process, whenever we have changes to the existing product or process, when we are doing just regular checkups. If, for example, a product has been on the market for the past 3 years or so, you might hear some reports of failures that you didn't anticipate. So you would just redo the FMEA for the future iteration of the product. Whenever you have an improvement goals for the product processes, and whenever you have new regulations, it's very important, especially with their environmental regulations. If your product does no longer conform to their environmental, let's say EPA, technically it is a failure mode because it is now damaging your environment, or at least from the legal point of view. So you will have to redo the FMEA then. And whenever you change a product function outside of original scope, you technically also need to do the DFMEA, which means that that example that we have with the paperclip in class, where we had to come up with different applications and users, we had to technically do their IDFMEA for that to make sure that we're not failing anything. And finally, we are if we want to just have a deeper understanding of what the failures are like for that product, or the process. And finally, on their design scale, on design timeline, that DFMEA usually occurs after you've done your preliminary design, so the prototype. However, you can do that earlier, and that's indicated that it's recommended to do it after function analysis, which is, I believe, what you are doing right now in PDR. Function analysis is basically figuring out what function your product is going to do, and what functions your components of your products are going to be responsible for. And finally, who does their IDFMEA? So yes, of course, it's going to be you as the engineering, and usually it's design engineers and validation engineers. However, the DFMEAs require a cross-functional collaborative team that includes all the departments affected. That includes engineering, manufacturing, quality, operations, procurement, purchasing, sourcing. In my time, we also include marketing for that reason, but we did. And the reason why is because all of those teams have a different outlook on your product. They have a different focus in mind, and they might think of the failures that you might not be familiar with just because they're experts in their specific field. So it's extremely important to get their input for this DFMEA so that you make sure that all the failures that you mentioned from covering all the bases, basically. However, because it includes all those people, those processes are usually very long, and the conversation can span starting from 3 hours all the way to 6, 12, etc., depending on how long their conversation is going to go. Finally, what we are doing the DFMEA on, or what our focus is their interfaces of any product. In their team interchange meeting, you looked at their interfaces and physical connections and material exchanges between the different subsystems, and that's where the design FMEA focus on. And to figure out all of those interfaces, we usually use some tools such as structure trees, block diagrams, boundary diagrams, flow diagrams, and other visualization tools that help us to figure out what is actually going on in the product. However, because all of those additional tools need to be done before the IDFMEA can be actually started, it creates a huge amount of prep work to be done before the IDFMEA can actually be started. So there is a lot of prep work, and then the whole process also takes a long, which is why starting it as early as possible is probably in your benefit. But let's move on to the IDFMEA format in general. We are just going to pay attention to their top part, so to their headings. So generally, those the format of their DFMEA tables look very similar. At least they have very similar components to them. Different companies can have some additional points to them or just remove some. But in general, we have the first about 10 points correct, the same every time. It is an industry standard. So DFMEA focuses on the functions. So we're going to write out the function that we do and their potential failure mode for that function. And after you figured out the failure mode or the way that failure can occur, we write out what the effect of that failure is. And then we have the letter S, O, and D. S stands for severity, or how bad it is that the failure is going to occur. Then we have O for occurrence, which is how often the failure is going to happen. And D for detection, or how easy it is to detect that the failure has occurred. And of course, we need to identify the potential causes of failure and the current process controls that we have in place to prevent the failure from happening. Finally, we have their RPN number in here that is a product of severity, occurrence, and detection scores. And it goes from 0 to 1,000. 1,000 is the maximum score. And that score is used to identify their points or the failure modes on which the team should focus on the most. So the higher the point, the more prominent the issue is. And so more effort should be put in place to prevent that failure from happening. For example, here, their team should probably focus on their 240 score, which is a internal jam alert for the machine jamming. I believe this is a ATM failure mode analysis. And finally, after you figure out the number, there is a column for recommended action. This is where you write out your preventative actions or how you suggest the teams or the engineers can prevent the failure from happening. And so let's go into their potential failure modes. So because we are thinking of the failure modes as a way the failure can occur in the state of their functions, we are having 7, and let's not look at the 8 now, 7 possible problems with the functions. Starting with there is no function happening at all, to there's degradation of function, or there's partial function, or even if there's exceeding function happening. And to give you an example, what could we give? Let's say the hose nozzle, right? If the sealing function, right? The hose nozzle supposed to be sealed. If it doesn't seal at all, that is clearly a loss of function or no function because it doesn't seal. But if it, for example, drips, that would be a partial function because it is sealing, but not to the full extent. And of course, the 8th one, we have the user is not satisfied, which is a failure mode, but that relates to the user only. And I like to give the example of their chair. The chair back is, the point of it is to be comfortable, right? That's why we included their back on the chair. However, the user can think that their chair back is too hard and he is not satisfied with the softness of it. That is technically a failure mode because the user is not satisfied with the outcome. Okay, and let's go into their ranking tables. So for all of their severity, occurrence, and detection scores, we're not just scoring them out of the blue. Their industry has created a industry standard ranking tables for severity, occurrence, and detectance, and they are currently taken in the manual of their potential failure modes and effects analysis. This one is specifically 4th edition. Every company may change them slightly to identify or to bring them closer to their specific product that they're creating. However, in general, they are very similar to this industry standard. So the severity one specifically, or how bad it is that the failure occurs, goes from 1 to 10, with the 10 being, oh, it's really bad. It is failed, it is affecting the safe vehicle operation, or involves non-compliance with government regulation without warning. And the 1 being no discernible effect at all. For example, in engine speak, any thermal event or fires is an automatic 10. And the reason is because there is no way to operate their vehicles safely when there is a fire in the engine. Another one that would be also a 10 is, for example, your urea tank broke, and now you're not conforming to the environmental regulations. That is also a 10 because you're in non-compliance with government regulations without warning about environment. In general, there's 5 different groups, which is the failure to meet safety and or regulatory requirements. There's loss, degradation of primary function, and loss of degradation of secondary function, and annoyance. So we all kind of understand what the primary and secondary function difference is. Primary function, for example, in the car is to drive. In the secondary would be AC. Right. If you lose AC, it's not a big problem because you can still drive. So, but it is a loss of the secondary function that makes their drive more comfortable. So I would probably rank that as a 6 because the comfort makes it reduced level performance, let's say 5. Just because it's reduced level of performance, it's the reduced level of comfort, but the vehicle is operable. Now for the annoyance, that is a little bit more about appearance and audible noise. And Dr. Trump likes the example of my personal ankle. I have a arthritis in it. So every time I make a step, well, most every time, it clicks, it makes a sound. It doesn't hurt. And I can still walk, jump, run, do everything, which is a primary and I assume secondary function. So it doesn't hurt. I can still do all of those functions, but it does make a noise and it is annoying. It doesn't make a noise every single step I make, but let's say half of the time. And that would be a 3 because it makes a noise. It's annoying to me. It's half of the time. However, if I was, let's say, working in the lab, and some other people started telling me your ankle clicks and we notice it and it's annoying to us, that would be a 4 because it is now noticed by most customers, not only me, but also other people. Okay, any questions on the severity? Okay, let's go to their occurrence. Occurrence, or how often their failure occurs, is probably the easiest one to explain and go. It goes once again from 1 to 10, with the 10 being it occurs there most often, and 1 being it does not happen at all. And as you can see on the right, we have the number of times or incidents per items per vehicle or per your product that it happens. So it's really easy to just pay attention to the numbers. If you don't have those numbers, which usually come from testing or other previous knowledge, then you can pay attention to the occurrence of cause information on the left. In general, for your FDR, you probably would be making some assumptions and paying attention to this second column. Okay, any questions about that? Cool. Let's move on to the detection. Detection, or how easy it is to find out that the failure has occurred, is also on the scale from 1 to 10. But the 10 here is now, it is not easy to detect it at all. We can't. Number 1, it does not happen just because we fully prevented it before. And the most important things about this specific ranking table is their differentiation between their detection happening prior to design freeze and post design freeze. So the design freeze would mostly be like your FDR, for example, where you have come up with already, you've prototyped, you've designed everything, you've come up with their design, and now you're no longer changing it. You've basically given that product out to different teams to deal with it, and you're starting your new project. So it's, as I said, well, when their cost and time, and the cost becomes exponentially more expensive with more time you spend on the project, it is important to detect the failures as early as possible. And that's why the prior to design freeze has a lower rank number than the post-design freeze. Those detections are based generally on their testing and on the different FEAs, on the other virtual analysis capabilities. So the testing can be done as degradation, test to failure, and pass fail, and those are repeated for the post-design freeze. Just it's a high number because it's now going to be more expensive to do. Okay, any questions? No? Cool. So because there are no questions, we are going to actually do a worked example ourselves. And before we do that, I need you to come up with a product that we're going to do the example on. Just if you don't like to speak, you can drop it in the chat, please. Could be anything that you can think of. The launcher. Let's start with something easy, not what we're doing for this for the FDR. Something out of your daily basis, like the door, for example. I don't know, something of that matter. Desk chair. Okay, it's a desk chair. Because it says a desk chair, let's just grab one subsystem for now and one function that we're going to focus on because we don't have a lot of time. So which part of their desk would you like to focus on? The desk chair. The wheels? Okay, we're gonna do the wheels again. All right. So what is the function of the wheels? I'm thinking there is one to support the person sitting, the user, and yes, to allow mobility or to move. So we're going to write that down. The first one is to, let's go, move. I can't type. Move the chair. We're going to go with the move the chair for now, and then we're gonna come back later for the support the user. So when you're doing your FDR IDFMEA, and you will be doing it only on one subsystem, not all, so choose the one that's easier. I recommend to, and you can see the Excel right on the right. Yes, great, thank you. Okay, so I would recommend writing every failure mode in a separate row so that you can calculate the RPN number much easier. It's just easier to do that. Okay, so the potential failure mode, which when you're looking at the left, let's think about there is no function. What failure mode would that be? The chair doesn't move. Yes. What about, let's say, partial function? Chair moves with difficulty. Yes. And let's do one more. Unintended function. Can you think of anything there? Sitting could be too. Exceeding function, maybe, if it, for example, slips under the person. So chair moves, chair scratches the floor. I don't think that is a failure mode. I think it's the effect of failure. Chair scratches the floor. But for now, let's go with the 3 that we have here. And let's go on to the potential effects of failure. Okay, so the chair doesn't move, the potential failure mode. What is the effect of that? It's no longer a mobile device. Yes, I would say maybe we could say that it is a user dissatisfaction because they clearly bought the chair to move and it doesn't move. What about chair moves with difficulty?
Would these all be user dissatisfaction?
Yes, but the chair moves too quickly has an additional point that we are looking for. For example, chair moves too quickly or slips under, right? If it slips under from under the person, let's say that.
Then you could have injury.
Exactly. Then we can
Right.
have injury. Yeah. Injury, then once again, injury. And then we're gonna add dissatisfaction here, but also we can say floor damage. Because if it moves with difficulty, it might scratch. There might be some marking on there. So once you've done with the effects of failure, let's go into the severity. And you should see it on the left and rank all the severity based on the effect. How bad it is that the user is dissatisfied that the chair doesn't move.
Maybe 6.
So what is the primary function of the chair then?
To allow the user to sit.
Okay, so if you're defining it like that, where their first primary function is to allow a person to sit, then yes, it would be a 6. If you said that, for example, moving chair is their primary function, then it would be an 8.
Okay.
Yeah. Okay, so we have a 6 here. How about user dissatisfaction, floor damage, because the chair moves with difficulty? And we already said that the moving the chair is the secondary function, so it should be somewhere between 6 and 5. But because the chair still moves, I would rank it as a 5. It's moving, just not great. What about the last one? What about injury?
Maybe 9 or 10.
Yes, so the difference between 9 and 10 in the severity is the warning that it gives. There is no real warning when their chair just slips. So I would rank it as a 10 because it is affecting their safe operation on it. And there's probably some safety standards that the government says, but I'm not sure on that. Okay, so once we've done that, let's go to the cause of failure. What could be the cause that the chair doesn't move? And specifically, we're looking at the wheels subsystem, remember? Yeah.
The wheel could have broken.
Okay.
Like, so maybe it only has part of the assembly still intact.
Okay. Oops, that's not how you spell intact. Okay, yes, that's correct. How about number 2? What could be the cause of chair moving with difficulty?
Something could be caught in the wheel.
Yep, that's great. Something could be caught in the wheel. Okay, and what could be the cause of chair just slipping?
Maybe an issue with the bearing or the surface that the chair's on.
The surface could be it, and we're gonna cover it a little bit later. Second. Oh. But also, I'm thinking maybe the bearing, maybe there's too much lubrication in the bearing. It's just too slippery. Okay, so once we've done that, we are going into their occurrence and ranking their occurrence now. So how often do you think it will happen that the chair doesn't move? And we're going to pay attention to the second column here.
Are we assuming that in this column, the wheel is broken?
Yes, sorry, should rephrase it. How often will we get a broken wheel that would result in their not moving chair? I would probably say something maybe like a 5, because the wheels do break, and it's an occasional failures associated with similar designs. Let's just say that we are creating a new chair, but we're basing it on their other different designs that we've had before with wheels. So the failures that do happen. So it's probably be somewhere a 5. Okay. What about something getting caught in the wheel?
That's probably maybe an 8 or 9.
Yes, so 9 would mean that we can't avoid that failure at all, which I'm not sure happens as much often. But I would say 8 is a good guess. The failure is likely with new design, new application, or change of duty cycle operating conditions. So once we go into the, for example, from the carpet to outside, really easy to get caught. Or even their different room where like hair can get stuck or something like that. How about occurrence of surface problems and too much lubrication in the bearing? And let's focus on the surface.
That you cannot really control for the surface, right? So then
we can and we can at the same time. While we can't exactly control where their user is going to place it, our ways of controlling it is by placing warning labels, by writing a user manual, by explaining and like making the user aware that he shouldn't be using it in the specific application, like ice, for example. Yeah, and those technically are their designs, engineers' responsibility to think about, specifically the warning labels that need to be put on. For example, their engine's rail or their accumulator that connects to their high pressure injectors, that has a ton of labels on it because it is important that the user knows that that is under pressure. And it's not really an engine company job to tell you not to use it not to open it when it's, for example, they're not we're not legally responsible if you open it and we put the label on. And at the end of the day, we're also trying to protect ourselves from the legal repercussions.
Right.
Yeah. So I would say that probably doesn't happen as often. And maybe it's a 6 and a 5. Yeah, so let's put it as a 6. Let's go to the current process controls. So what kind of processes do we have in place for the broken wheel? So to prevent the broken wheel from happening. There also might not be any. It's just could be just that. If there are not any,
could we include material selection in something like this?
We could, yes. Material selection is a good choice, and usually that would be governed by whenever you fill it out in the industry, you would say material selection per and some kind of standard CES and 5 numbers, and that would be the standard number that guides you through the process for this application. So that's a good point. That is a good selection. What about their process control for their something getting caught in the wheel?
Maybe controlling the clearances in the wheel?
Yeah, that could be it. So that also could be a standard. So let's say standard clearances per some kind of standard. Let's name it that way. Okay, and surfaces, current process controls. As I said before, we usually place warnings, warning labels, user manuals, etc. etc. And finally, let's go to the detection score and quickly rank the detections. So how easy do you think it is going to be to find the broken wheel, specifically in the design process?
Assuming it's broken while you're designing.
Assuming that it's broken while we're testing our designs.
Okay, so the most easy.
Yeah. Well, so testing, there are different cycles of testing. There's testing done on the prototypes, and there is also testing done after the prototype has already been approved, right? And the difference is between prior design freeze and post. So when do you think we will be able to figure out that the wheel breaks?
Probably prior to design freeze.
Yeah, I think so too. And I think it is probably a degradation testing, just because we probably will be moving the chair a lot and figuring out when their wheel breaks off. So that would be a 3. What about detecting that something got caught in the wheel?
Maybe let's see. Maybe also in that prior to design freeze, maybe a 5.
Yeah, I would agree with you. 5 is a good choice because it's a pass-fail testing. And finally, when the detection is for the surface. I personally think we can't control that because we cannot detect it. So it would be a 10. Yeah. So that means that the RPN number here is very low. Let me see what's going on. Shouldn't be that. Oh, it's a plus. Sorry. Should be a multiplication. There we go. Okay. So we have the RPN number. And that RPN number shows us that the highest score is for that surface protection, right? So we have the 600, which is what we should be focusing on to prevent. And that's where you would write the recommended action for. So at the moment, you would think, yes, there are warning labels and user manuals, so maybe that is actually enough. And sometimes the whole cross-functional team will give you an okay to go ahead with what you have at the moment, just because you have enough warning labels. However, because the severity is at 10 here as well, I would say maybe we could have a redesign, or maybe we have a coating, some kind of anti-slip coating or something similar. No, that's not how you spell that. Okay. So, and this is, you're going to go with this process for every single line that you have in your project. And for yours is going to be just one subsystem. Just choose one function of that subsystem, but you need to cover the all components that perform that function as well. But other than that, this is what their DFMEA is like. So if you have any questions, please let me know. But if not, I think we're good to go.
I have one question about FMEA. So I learned about this concept when I had a co-op with Cummins.
Okay. Me too.
Okay. So I was wondering if you know if this is like a standard across many companies. I know root cause analysis is a standard, but is there a lot of people that use FMEA in particular?
Yes, it is very used. So the problem with the root cause analysis is that it's done after the failure has already occurred.
Right.
And so that usually means you know, either, let's say, the worst case situation, let's say, their product is out in the market and then the failure occurred. That means they're probably going to have to pay for warranty. They're going to pay for their time for the technicians to fix that problem, for your time to redesign it, for the other people's. And that's the problem with their root cause analysis, just because it's focused on after the fact. Their FMEA is used really widely. Generally, they're like iterations of it done, and it's done as early as possible so that you can just avoid some design flaws that you just may not think about. I think I have some friends who have had internship with like Lockheed and Honeywell, and they did that there as well. So it's very used.
Okay. Okay.
Yeah.
Yeah. And one of my projects, when I was working with Pratt Whitney, was going through root cause analysis as well. So it
Yeah.
seems like it's a kind of a standard.
It is. Yeah.
Okay. Yeah.
Cool. But thank you
Cool.
for coming in here and collaborating. That was
Of course.
really fun to have. But yeah, I think if there are no more questions, then you're free to go.
Thank you.
Thanks. Bye.